For part B, we do a similar process. So now we have our capacitor and the resistor switched, and we will now see that it actually behaves very differently from the low pass filter. Okay, so now we want our transfer function, which is just, so this is still a voltage divider, so we still use our equation. For our voltage divider. And we notice that dividing by Vn, we notice that our transfer function is just equal to this coefficient. So plugging in the values for our impedances, we now get this as our transfer function for the CR circuit. Now, when omega approaches 0, our magnitude of the transfer function is just the magnitude of RC, okay. The magnitude of J omega RC over plus J, 1 plus J omega RC. But we realize that the denominator, the numerator goes to 0, while our denominator goes to 1, so non-zero. So that means as omega approaches 0 in the limit, our magnitude is just 0. Our transfer function is just 0, and the magnitude of 0 is just 0. So for a small omega, we have a 0. And that means our V out is just 0. Well, that's an opposite behavior from our low pass filter. Let's move on to when omega approaches infinity. So in this case, this becomes infinity and infinity. So infinity over infinity is undefined. So in this case, we use the L'Hopital's rule and take the derivative of the numerator and the denominator. So this is just equal to okay, I'm just gonna find, okay. We take the derivative with respect to omega for the numerator and for the denominator separately. So we lose 1 because 1 is not dependent on the omega. So it's just 0 when we take the derivative. And this cancels out to 1. So that just means when we have omega approaching infinity, our V out is almost equal to our V in. So that gives us an opposite behavior from the low pass filter. And we call that, in fact, when we have, we call that a high pass filter. And we see why this terminology is selected. Because when we have a high frequency, we see that our input voltage almost all passes through and gives our output voltage. However, when we have a small frequency, then our V out is almost 0. So that means we don't have any frequency, any voltage, and the voltage is blocked in the middle. Okay. Next we have the cutoff frequency. So the cutoff frequency is when our j omega RC over 1 plus j omega RC, the magnitude, is equal to 1 over root 2. Well, so we probably want to solve for the magnitude, which is just the magnitude of the numerator, omega RC, over the magnitude of the denominator. And this should equal 1 over root 2. So we solve for this equation. And when we square both sides, we get this. So we finally get 1 over RC as our cutoff frequency. Yeah. So that would be all for question 3, part B. If you have any questions, drop down in the comments or send me an email if you know me. Okay.